Alright, hello. So, until now, our robot was just a visual model in RVs. It looked nice, but it wasn't alive. So now we move to the next level. In this module, we're going to use Gazebo, a real physics simulator. So gravity, collision, mass, inertia, everything becomes real. This is where your robot stops being a drawing and starts behaving like a real machine. So, what is Gazebo? Gazebo is a 3D robotic simulator. It provides a physics engine, realistic sensor, custom environments, direct integration with ROS2. This is important. ROS2 JZ use Gazebo Harmonic. This is the newer generation version. That is why we use the command GZ instead of the old Gazebo. Even if Gazebo is installed, we need the ROS2 integration packages. These packages allow Gazebo and ROS2 to talk to each other. So our URDF works perfectly in RVs, but Gazebo is different. RVs only visualize, Gazebo simulates physics. And here's the key, the differences. URDF materials don't work in Gazebo. That's why Gazebo needs special Gazebo tags. If you don't add them, your robot will appear gray. We will not modify our original robots file. Instead, we create a new Xacro file specifically for Gazebo. Why? Because simulation-specific element should not pollute the pure robot description. This is a very important architectural concept. We reuse our base robot using Xacro include. We don't rewrite the robot, we extend it. These Gazebo reference links tags override the visual appearance inside Gazebo. Notice something important. They reference links by name. This means your link's name must match exactly. Very important debugging tip. This is the important part. We are loading the Gazebo ROS2 control plugin. This plugin allows Gazebo to connect to ROS2 control. Without this, your robot will spawn, but joints won't move. That line is powerful. Now we define the environment. Gazebo does not use URDF for worlds. It uses SDF. SDF describes the simulation world, the physics, the lighting, the ground objects. This defines simulation precision. Max step size is equal to simulation resolution. Smaller, more accurate, but heavier. Plugins. These are the core Gazebo systems. Without them, physics and visualization won't work properly. Ground plane. If you don't define collisions here, your robot will fall forever. Table model. This is optional, but it makes simulation realistic. Notice we use static true, so it doesn't fall. This is the most important part. The launch file process the Xacro, start Gazebo, spawn the robot, start robot state publisher, and creates a bridge between ROS2 and Gazebo. This is real robotic architecture. This is these lines connect everything. So here in the launch file, we can see the package path. So we locate package directories dynamically. Never hardcode absolute paths in ROS2. This is a best practice. Xacro processing. This line converts the Xacro into a URDF string at a runtime. Gazebo never sees Xacro. It sees processed XML. This is a critical concept. We have a robot state publisher. Even in simulation, we still need robot state publisher because it publishes TF transfers. This is a key architecture reminder. Uh, it also includes Gazebo. This includes Gazebo official launch file. We pass our world file as argument. The R flag means run immediately. We also have the robot spawn. This node reads the robot description topic and inserts the robot into Gazebo. The Z flag places it on top of the table. If you set too low, your robot explodes into the table. Bridge. This connects the Gazebo clock to ROS2. Simulation time is different for system time. Without this, your nodes may behave incorrectly. Very important. Launch file, walls, and URDF must be installed into the shared directory. If not, ROS2 cannot find them. Here we have the same bug that you have before. Uh, we have an error because we add in the CMake list the folder config and if he doesn't find them, he triggers an error. So we just create the folder or we delete it. So you should now see the Gazebo world, the table, the robot arm, and the physics running. If your robot falls, you forgot collision. If it's great, you forgot Gazebo material. If it doesn't spawn, check spawn nodes. Also, as you see, I have an error, and it's because I was not using OpenGL, so I put the flag on 1 so to correct this. So in this module, we transform a static robot into a simulated robot. We learn how Gazebo differs from RVs, how to extend URDR for simulation, how to build a world, and how to span a robot dynamically. This is the bridge simulation and ROS2. Now the robot exists in physics, and in the next module we make it move.